So in section 7.1, we're going to work on estimating a population proportion. Now, as we ramp up and get going in this section, let me remind you of a few things here. We have different notations for our samples versus our populations. So for instance, if I was taking a sample and I calculated the mean, I don't remember what notation I would use for that. What do I write here for the sample mean?
X bar.
X bar, well done. Thank you, Joe. How about someone else for the population mean? Remember what that? These are your Greek letters over here, at least some of them.
Is it mu?
Mu. All right, cool. Thank you. Now let's move over to standard deviation. Standard deviation is represented in the sample form by a...
I don't remember. What is the name of it? It looks like
It's a mu. It's a Greek letter. It's a Greek letter M. It's called mu.
Called mu. Okay.
Mu. So that's the symbol that we use there. That's if you have all the data in your population and you're able to calculate the mean for everything. Likewise, there's a Greek letter sigma that we use to represent the standard deviation of the entire population. Now, if you don't have the entire population, then you have just a sample. Then we're going to use S to denote the sample standard deviation as opposed to the population standard deviation. And the last one is what we're going to work on here today is our population proportion, P hat. Now, that's the proportion of successes in your sample, and that's going to estimate P in your population. And I'm not happy that P just gets used so much in a stats class, but I'm hoping it's something you're going to get used to and it's not going to bother you. Now, this is called a point estimate. And what we're hoping for in general is that whatever we're estimating, if it's a mean, if it's a standard deviation, or if it's population proportion, we're hoping that we get a good estimate of the parameter. Typically speaking, you don't know the parameter. You don't know what this is, but still we kind of want to find out information about it. We want to have at least a good guess as to what these things are. And let me do a kind of example of something like that. So for instance, we could try and figure out what percentage of the earth is covered by water. It's a good question. Some people might have a good idea, but let's see if we can't figure it out. And the way we're going to figure it out, at least try and estimate it, is this. I've sent you a link to a website called random.org. And in it, they've got a little applet that allows you to pick a random coordinate someplace on Earth. You click that, and what I want you to do is I want you to keep track of your guesses. So let's see, successes and trials. So every time you land in water, that's going to be a success. And then you do another tick here for trial. So my first one, well, I got a trial. I'll put one there for trial, but I didn't land in water. I landed on land. And then we'll do it again. And yeah, that looks like, let me kind of zoom in a little bit. Yeah, that looks like land. All right, you're between Costa Rica and yeah, someplace else. All right, but it looks like land. So I'm like 0 for 2. You're going to keep on clicking and get as many of these as you can. So now I'm 1 for 3. So try and get as many of these as you can. I'll give you a couple minutes to work on this. And we're going to put in our data and take a look at it and start getting used to what it means to try and estimate a population proportion. Because that's what we're doing. Is we're collecting a lot of different estimates of this p hat or different estimates p hat, but overall we want to find out something about the population proportion. So we'll see here. Okay, so we've all entered in some data, and what we're interested in this particular example is to find out the proportion of times that we landed in water. So what I can do with Google Sheets is just calculate that proportion like this, equals, click the number of successes divided by the number of trials. All right, now I don't want to divide twice. There we go. So 71%. And the nice thing is that I can just do this now for everybody. Uh-oh, somebody put in something backwards, I think. All right, so there we go. Now, what you're seeing is that you're getting all kinds of different estimates for the proportion of the Earth's surface covered with water. And I'm thinking that, yeah, there we go, 19. That looks a little better. Because 110% of the Earth's surface covered by water might be kind of tough. So all these different estimates. Now there's only one true answer. We don't necessarily know what it is, but there's only going to be one answer. And that's kind of a problem. All these are different estimates. Which one's right? Or what do you do when you give somebody an estimate? Because if you sampled again, you're going to get a different estimate. So how do you handle that? Well, the way you handle that is you allow for a little error. And we're going to create a confidence interval. So a confidence interval for a population proportion for P, the population proportion is given by this. You're going to take p hat minus a little bit, minus some error term, and p hat plus that error term. So as a reminder, p hat, that's going to be your sample proportion. And then E is going to be an error term. And what you're doing is you're saying, you know what, I know that if I did different samples, I'm going to get a different sample estimate, a different point estimate, but so that I have a good idea overall what's going on, I'm going to create this confidence interval from here to here and say, you know what, I think that the true population parameter is in here someplace. So that's what we're going to do. Now, to get acquainted with that error term is going to take a lot. There's a lot that goes into that error term. And it's going to be a chance to review some things from section 6.2. It's also going to be a little bit new as well. So we're going to have to work on figuring out what that notation is. But let's take a look back here and try and see a little bit about what we ended up with. Now, what I'll do, because we didn't get quite as much data as I might have wanted, is I'm going to add up the data from all of my classes. So it'll be the sum of not only our data here, so up to there, I'll put in a comma, then add in the class right before yours. A little bit more, not quite that high, comma, and then my night class, which starts here and goes up to there. There we go. So, wow, now I've got a lot of data to work with, and I appreciate your part in this. I want to do that same thing over here. The clever way is just to copy that cell over to here. There we go. And let's see what that gives us in terms of a proportion. So that's going to equal this divided by this. So, wow, quite a lot of samples. So we got that 69% of the Earth's surface is covered with water. Now, even though there's a lot of samples that went into that, it's probably not exactly right. So we want to surround that by a confidence interval so that we can say, you know what, 69% is my statistics class best guess, but because we know that it's probably not exactly right, we'll surround it by a confidence interval. So let's figure out how to create that confidence interval. All right. So I'm going to need to introduce you to a lot of notation here. And let's do that. Let me come over here. So part of the notation is going to be some review from a previous section 6.2. So overall, our goal is to calculate the error term. And I'll give you a look at what that is so that you can appreciate all the things we're going to have to calculate and all the things we're going to have to understand. It's going to be z sub alpha over 2 times the square root of p hat times q hat over n. Now let's start with the hard part first, the z sub alpha over 2. Anytime you have z sub alpha, it's going to refer to a spot in a normal distribution, the standard normal distribution with that much area in the right tail. So let me draw that. Not so great, but not too bad. So we just got a little area here in the tail. And that area is going to be that. So this is z sub alpha over 2. So it's the point in the right tail with that much area to the right. Now, how do you find that? Now, there's a couple ways you can find that. It depends if you're working on Google Sheets. Remember, Google Sheets is actually going to work with the area to the left. So Google Sheets is going to work with this area, which, okay, we can do that. If you got that much in the right tail, then 1 minus this is in the left tail. So the rest of this would be 1 minus alpha over 2. And in general, your command on Google Sheets is going to look like this. That's going to be equals norm inverse of whatever this is, however much area that is. In fact, I'll put it in blue to kind of show you that correspondence. 1 minus alpha over 2. So that's coming right from here, comma 0, comma 1. If you're doing this on your graphing calculator, your TI-84, it's going to look a little different. There, you're going to use the command inverse norm. And again, you're going to talk about this area, 1 minus alpha over 2. Comma 0, comma 1. Now you actually do have some more flexibility with the graphing calculator because sometimes if your graphing calculator is up to date, it'll actually let you find areas in the right tail or in the center. So there is more flexibility there. But for consistency, I'm going to write it like this. We'll practice that for one of these calculations. Let's see what else. Well, one of the things you're going to need to know is what this alpha is. And so let's talk about alpha for a second. Alpha is going to be what's called the level of significance. Alpha equals the level of, not UG, of, sorry, level of significance. There we go, never happened. Of significance. And 1 minus alpha is going to be your confidence level. So if you have one, you have the other. If one of them is 3%, the other one's 97%, that kind of thing. Now, in our first example, we're going to do alpha is 0.05, and then 1 minus, which is also 5%. 1 minus 0.05 would be 0.95 or 95%, which is a common level that you're going to see a lot as you work through this course. That's our level of confidence. What else? Some other things. So some more notation. N is going to be your sample size. X is going to be the number of successes. Number of successes. P hat is going to be X over N. That's going to be the proportion of successes. So your sample proportion of successes. And then there's going to be Q hat. And the easiest way to calculate Q hat is it's going to be 1 minus P hat. This is much like what we dealt with the binomial theorem, or the binomial random variables. So proportion of failures. Nice. So a lot of notation to get comfortable with here. But let's practice calculating at least one of these right now, and that's going to be our z sub alpha over 2 when we're dealing with the 5% level. So let's find z sub alpha over 2 for alpha equal 0.05. Okay. Well, that's going to mean I have 0 or z sub 0.05 divided by 2. And you can take out a calculator if you're not comfortable. That's z sub 0.025. And I want to find that from my z distribution. So the good news for you is that this is really review stuff for you in advance of your test on Tuesday from section 6.2. So let's see. That's going to be the point on the z distribution with 2.5% of the area in the right tail. Now, based on the way I've drawn this, let me ask you a question. Is z going to be positive or negative?
Positive?
Yeah, positive. Because this middle number here is 0, and it has to be to the right of 0. So you can calculate that a couple different ways. Let's do it first of all on the graphing calculator. So Let's clear this out. You can watch my calculations here or my keystrokes. Second distribution, we want the inverse norm. So let me go with that. 3. The area that I want is going to be 1 minus 0.05 divided by 2. Or if you wanted to just type in and figure out what that is, that's going to be 97.5%, because that's going to be the area in the left tail. Now, the reason I'm doing it that way is because that's how people who do Google Sheets are going to have to work with it. If you're doing this command off Google Sheets, you have to put in the area of the left tail. So that area in orange is 0.975. All right. If you don't want to think, then you can type it in like I did. If you do want to think, you can type in 0.975. The mean is 0, the standard deviation is 1, and that's the area in the left. Scroll down 1, press enter, and bam, you got it. Now, with the graphing calculator, you actually do have a little bit more flexibility. I could have just done this. Like I said, you know what? I want 2.5% of the area in the right tail and save myself the bother of that kind of calculation. So I should get exactly the same thing, about 1.96. Nice. Now, for those of you who like Google Sheets, hey, I don't want to leave you out in the cold as well either. So that would be equal inverse norm, or excuse me, norm inverse of, let's see, 0.975, comma 0, comma 1. There you go. So about 1.96. You should be able to get that number one way or another. So let me pause. Are we comfortable getting that number? I mean, that problem right by itself, getting that number, is a good question for us on Tuesday. The difference is that on Tuesday, you'll have probably a different mean and different standard deviation. Jaleisha?
I got a question. So we don't do anything with the 0.025?
Yeah, actually we did. We kind of did. Because that 0.025 was really, you know, part of this area. It was this area here to the right, which also means this area to the left. So we take 1 minus this, and it gives you that. So yeah, we did use the 0.025. Is that answering your question? Okay. If you have a follow-up, let me know. All right. Let's try and put this together and do an example, and then we'll look back at our own example. We're going to start with example A from that handout that I sent out. So that's going to be here. Okay, so let's just read the top part. It says, use the sample data and confidence level given below to complete parts A through D. A research institute poll asked respondents if they felt vulnerable to identity theft. In the poll of 1,020, 590 said yes, use a 90% confidence level. So, okay, let's do that. Actually, you know what? Do you guys have a different example A? Or is this the example A that you've got? All right, we'll go with this one. So let me highlight some of the important information we need here. We need N, we need X, and we also need our level of confidence. So this is using 90% confidence level. Okay, let's do it. So those are the things I'm going to write down. Example A. And N equals 1,020, 590, and 90%. Okay, so this is what I got. Now, I'm going to need a lot more here in order to calculate things. I'm going to need, for instance, P hat. Now, P hat is going to be X over N. So 5,090 divided by 1,020. So probably around, 58% or something like that. Let's take a look. So 590 divided by 1,020. Yeah, about 58%, 0.578. While I'm here, I might as well also get Q hat. So for Q hat, I can do 1 minus, and then if I hit the up arrow key, it puts me on my previous calculation. I'll just press enter to bring it down, enter again to have it do my calculation. So Q hat equals 1 minus P hat. And that gives me 0.422. Nice. What else am I going to need to know? Well, I'm going to need to know, first of all, what alpha is. And alpha is going to be 1 minus my confidence level. So that's going to be 1 minus 90%, 1 minus 0.9. What's that going to give me for alpha?
That would be 0.1, wouldn't it?
Thank you, gentlemen. 0.1. Yeah, 0.1. Now I need that because eventually I'm going to need to calculate E, which is Z alpha over 2 times the square root of P hat Q hat over N. So right now I'm going to focus on calculating Z sub alpha over 2. Now for us, that really means Z sub 0.01 divided by 2, or 0.1 divided by 2. And if you don't trust yourself, hey, there's no shame. 0.1 divided by 2. There you go, 0.05. Get it right. A lot of people, mess up with the decimal there someplace, and that's not so good. Z sub 0.05. So this is where you can test yourself again. Z sub 0.05. Where should I draw that? In the right tail or the left tail?
Right.
Right tail. Good job. That's going to be the point with 5% of the area in the right tail. Look that up. I'm thinking it should be about 1.645, but hey, I was never very good at math, so help me out. That's on the right alpha on the right area. So you can get this number either off of Google Sheets or your graphing calculator. And actually, we can get it off of statdisk as well. So we got an area of 0.05. That's going to mean the rest of that area to the left of this is 0.95. So it's going to be 1 minus 0.05 or 0.95. And again, you can get that on Google Sheets. I'm just going to take my previous calculation and modify it. I'm going to put in 0.95. And there you go, 1.645. You should be able to get that either on Google Sheets or on your graphing calculator or on statdisk, which I'll have to show you at some point. Wow. I think we got all the stuff we need to put this together. Our eventual goal in something like this is to develop a confidence interval. So our confidence interval has the form p hat minus e to p hat plus e. So the first thing I need to do is I need to calculate, well, what is e? All right, that's a good question. Let's figure out what e is. E is going to be z sub alpha over 2 times the square root of p hat q hat over n. And we've got all this information. Right there. That's my z sub alpha over 2. It's 1.645. What else did we need? We needed p hat. And p hat, that's all the way up here, is 0.578. So let me put that in here, 0.578. And then q hat was 0.422. So there's my q hat. There's q hat up there. There's q hat down there. And I hope I'm running out of formula because I'm running out of pens. I need n. N was 1,020. So let's put in the n there. And I think we're finally ready to calculate this thing. 1,020. Now keep in mind that just a few years ago, students in this course were looking up this number by hand in a table. Ugh, yuck. And that got even more confusing. So we're going to start making this whole process a lot easier. But we have to calculate this thing first. This is our margin of error. So I'll do it on my emulator here. Let's clear this out and then clear this out as well. So it's going to be 1.645 times, and you know what, I don't think I need to hit the times, my bad. Could have saved yourself a keystroke. Second, square root of 0.578 times 0.422 divided by 1,020. Yay. So about 2.5%. So about 0.0254. So that's your margin of error. And what you could do at that point is create your confidence interval. So our confidence interval is going to be between p hat minus e and p hat plus e. So our confidence interval let's see, it's going to be of this form, p hat minus e to p hat plus e. So what was p hat? P hat was 0.578. Let's do this on our calculator. And if you need to borrow a graphing calculator, let me know. But we'll type in 0.578 minus 0.0254. And that's my lower confidence limit. So about 0.05 or 0.5526. Okay, cool. Let's try the upper limit. So kind of a cute trick. If I hit second and then enter, it'll bring up my previous calculation. I'm just going to go back and make that a plus now. I call it economy of movement. There you go. So 0.6034. So there's your confidence level, confidence interval. So somewhere in there, we think the true population proportion lies. We don't know what it is exactly, but it's probably in there someplace. All right, lots going on here. We're about to make this a lot easier, but you should understand all this different notation and stuff like that. And you should be able to get all these various parts. Now, am I going to ask you to do this stuff by hand like we just did? No, we're going to make it easier. But before I move on to make it easier, are you okay with all this notation, what it means? N, X, P hat, Q hat, alpha, 1 minus alpha, and then our error term. All right, like I said, let's make this like a lot easier. So what I want you to do is I want you to open up statdisk and statdisk. What we're going to do is we're going to start out with the analysis tab. And then next go to confidence intervals. And from there, you're going to want proportion 1 sample. So that's where you want to go on statdisk. And I'm hoping that's going to make our life a lot easier. In fact, let me circle that. Beautiful. And here it is. So let's see, that only took us like what, 10 or 15 minutes to work through that calculation? Let's check it out on Google or on statdisk. We want a 90% confidence level, so 0.90. Our sample size was 1,020, and we had 590 successes. So, bam, there you go. Wow. Take a look at that. It's giving you pretty much everything. You've got the margin of error, which they calculated as 0.02543. And boy, that matches what we calculated pretty nicely, 0.0254. Take a look at the confidence interval. The confidence interval, what we're ultimately looking for, is right here. And here it is right here. Exactly the same as we got. Well, maybe not quite, but close enough. Yeah, close enough down to 3 digits. So, cool. So, I was kind of expecting a lot of ooh, ah, because this is really nice. I mean, it's just so much nicer to do it this way. Let me ask you a question. This is a 90% confidence interval. What if I wanted a 95% confidence interval? What do you think is going to happen to my margin of error or to the width of my confidence interval? Am I going to get a wider confidence interval or a smaller confidence interval if I want to be more confident? What do you think?
I would say smaller.
Yeah.
Smaller? Okay. A lot of people think that way as well. All right. Let's see what happens. Keep an eye on the error term. The size of the error term is also going to be related to the width of the interval. So let's put in a 95% confidence interval. Watch what happens to the error term and the width of the interval. Which way did it go? Did it get wider or did it get narrower?
Looks like it actually got wider.
Yeah, it looks like you get wider. Tell you what, let's try it again. Let's try 99% confidence level this time.
Yep, wider.
And it's definitely getting wider. And the reason is, if you want to be more confident that this interval contains the true population proportion, you got to give yourself more room for error. You're making your interval wider because you're allowing for things to be off by a greater margin. In fact, if you look at the last 3 calculations, margin of error has steadily gone up from the 0.9 level of confidence to the 0.95 to the 0.99 level of confidence. It keeps on marching up. And every time it marches up, this interval is going to get wider. Nice. Whoops. I didn't know I could do that. Okay. How are we looking on example A there? All right. Let's go back and take a look at our estimates now of the surface of the Earth, the percentage of the surface of the Earth covered with water. Now we know that 0.69 is probably not going to be the exact answer, but this is going to be our, that's going to be our point estimate. What I want to do is I want to surround that with a confidence level. So I'm going to calculate an error term. Error, so just E. And then from that, I can do P hat minus my error term, and then P hat plus my error term. So to get my upper and lower confidence levels. Now, I'm just going to use a 95% confidence level because I've already got my level Z alpha memorized. All right, that's 1.96 for a 5% level of confidence. So it's going to be 1.96 times P hat times Q, or square root of P hat, Q hat divided by N. And in our case was like pretty big. We had 1,085 observations. So that should give us a nice narrow range here. 1.96 times square root of, let's see here. It's going to be P hat, which is this, times 1 minus that. 1 minus that is going to be our Q hat, divided by N, which is all the way over here, like that. So that's my error term. So that's pretty good. That's 2%. That's a very small error term, and that's because we have a lot of observations. So good on you guys for hitting the refresh that often. Now, let's take our estimate and form our confidence interval. So it's going to be my point estimate minus the error term, and then my point estimate plus the error term. Now, in our modern age, when we don't know the answer to something, how do we find it out? What's the modern way to find out the answer to a question, like how much of the Earth's surface is covered by water?
Ask Google.
Yeah, ask Google, right?
Google it.
Google knows everything. Google it. And here we did. So 71%. Yay. So how do we do? Well, let's take a look. You know what? This one doesn't look right. Oh, because there's a minus there. How about if I put a plus there? Yay.
All right.
That rounds up to 71%. We hit it. So, I don't know, depending exactly what the confidence interval is, it does look like our confidence interval barely contains the true population proportion. Now, we can't always look up on Google what the true population proportion is. So that's why we rely on confidence intervals to say, all right, I know if we took a different sample, we'll probably get something else. But, you know, what do we think where do we think the true population proportion is? So that's nice. That's, by the way, that's why in national polls, when you look at polling data this fall, this semester, this election season, you'll see a lot of times with good poll results, they'll tell you the margin of error. And that margin of error is exactly this term we're calculating right now. And with a large sample size, you should be able to get your margin of error down to around 2 or 3%, well, 3 or 4% probably in a lot of national polls, which is pretty good. All right, it's not any guarantee. We saw that in 2016, but it's pretty good. Okay. That's a good little intro to this. We're going to do some more here, but let me take a break and give you a break as well.